Now let's talk about derivatives of log functions, which are similar to exponential functions, but with some key differences. Remember how log functions are related to exponentials. They are inverse functions. So how do we get derivative of ln of x? For now, we'll take this for granted, that it's 1 over x. Later, maybe in chapter 5 or 6, we'll take a look at the graphs and how they're related and how we can figure out that it's 1 over x. But it is true, derivative of ln of x, which if you recall, ln of x is the log base e. Let me write this. So ln of x, if you notice, this is the dedicated button that we'll use on your calculator, but it's a log base e. So once again, just like with e to the x, which was more straightforward, ln of x is also more straightforward. It's just 1 over x. Now let's take a look at derivatives of log of different bases. Let's say base a. Now notice it's very similar, but it's 1 over x. The only exception is ln of a is in denominator. So remember, with exponentials, ln of a was in the numerator together with the exponential. There was no ratio. The logs, the only difference is you have x in denominator together with ln of a, for example. Okay? So let's take a look at different derivatives. So again, ln of x is very straightforward. But what about y equals to log base 2 of x? How would we take derivative? Well, we'll just use the formula above. It's 1 over x, and since the base is 2, it would be times ln of 2. And again, you can use parentheses or not, but this is what it equals to. Now let's take a look at chain rule, because as before, you can have a ln of function anything more complicated than x. So really any other function. And again, we can try building it the same way that we did instead of memorizing all these formulas. It's a lot to memorize. Let's take a look and think of the ln as the outside again. And the f of x is the inside. And again, it's similar to the power rule when we used it. So f of x is inside of ln or inside of exponential. So again, I like to build it like this. I know the book gives like a kind of a shortcut formula, but I like to build it this way. I first put 1 over the function, which is f of x. So that's the derivative of ln of f of x, times, then I do the derivative of f prime of x, and sometimes you can simplify it, sometimes you cannot. And so later you put f prime of x in the numerator and f of x in the denominator. Again, this makes sense to me to multiply and then simplify them. This may create an extra step, but this is how I remember the chain rule. Now, it's kind of a little bit awkward to start with f prime of x first. But again, whatever works for you, you can build it the same way. Notice you have a formula for log base a very similarly. Again, we have 1 over f of x times ln of a, and that's the outside function, times f prime of x, which is the inside, derivative of the inside. And again, f prime of x can go in the numerator. And from then on, we can pretty much take derivatives of any log functions. Let's say if we have y equals ln of 8 times x, or 8x. Well, again, it's good to identify what f of x is, which is 8x. The derivative of 8x is 8. And notice I did use a shortcut formula, but really it would have been 1 over 8x times 8. And so the 8 can cancel. And notice how we end up with 1 over x, which is similar to derivative of ln of x, the simple ln of x. Now this would actually be true if 8 instead of 8 we had any constant times x. If we had 6x, then we'll have 6 over 6x. 6's will cancel. You'll get 1 over x. If we had 5x, it would be the same thing. Any constant times x, you'll still get 1 over x just because it simplifies. Okay? However, it's not true in general, which is why we still need the chain rule. What if we have y equals ln of 8 minus 3x? Again, here is the function and the derivative. Again, I use the shortcut formula, but it makes sense to me to have 1 over 8 minus 3x times negative 3. This is how I start sometimes. So the y prime equals to 1 over the function, which is 8 minus 3x, times negative 3. So this is how I start. And then I look, can I simplify anything? I'll just put the negative 3 on the top over 8 minus 3x. And then I'll look, see if we can simplify it. We cannot actually simplify anything because 8 minus 3x, there is a minus here. We're not multiplying, so you really cannot break it up and cancel with a negative 3. As tempting as it may be, this is actually the final answer. Okay? So this is how I usually work this out when I'm working the problem out. Now, what about the third example? Y equals ln of square root of x plus 5. This is a bit more challenging problem because you have a chain rule within chain rule, which is interesting how that happens. We have square root of x plus 5 equals to x plus 5 to the 1/2 power. I'll show it to you this way, but it's not very straightforward. Remember how to take the derivative of this from 4.3? Well, the 1/2 comes down. Then we have x plus 5 to the negative 1/2 power. So we can break this up. Notice how we have the derivative on the top, the original function on the bottom. And because it's a negative 1/2 exponent, we can put it in denominator. And negative 1/2, notice how we have negative 1 in the numerator and 2 in denominator. And what's happening to these two similar terms? Well, a square root times square root, or 1/2 plus 1/2 essentially, because you can add them when you multiply. You'll just get 1. So notice that's why the 1/2s disappear, which is why this is why it's the final answer. Also, square root of x times square root of x is equal to square root of x squared, if you recall, and they cancel each other, so it's x. So that's another property we can use. So you can work it this way. Put the work out the original function and the derivative, put the derivative over the original function, then move the 2 and the negative exponent in denominator, then simplify it. So you can do it this way. Or notice how we can use this property of the logarithm. So let me show you. First, I'm going to rewrite it as 1/2 power because square root is 1/2 power. Now, there is a property of logarithms that states that any exponents, a log of the exponent, can come to the front and become a coefficient. This is the property of log base a of x to any power, let's say r, is equal to r times log base a of x. So notice simply, it's like power of a power. If you remember way back from college algebra, power of a power becomes multiplication of powers, and logarithms are basically exponents. So anyway, if you remember this property to take the exponent down, then the derivative is much more straightforward because y prime would be 1/2, because that's the constant, times, so what's the derivative of ln of x plus 5? Well, it's 1 over x plus 5 times derivative of x plus 5, which is 1. So notice we end up with, am I missing a negative somewhere? I think I am. Let me try to think about this. Oh, I noted the typo. My apologies. This should be positive 1/2. I'm not sure where I got the negative from, but see how there is no negative in the derivative, so there should not be a negative. Otherwise, yeah, I'm like, why is that not working? So anyway, to finish this example, we'll have 1 over 2 times x plus 5. So notice how much easier was it to do it this way, for example, than this way. So again, this should not be a negative. You'll have a positive here. All right. And so this is how we can do that example. So I think it's easier if you bring the exponent down and make it coefficient. But again, you can practice it either way. All right, let's take a look at another one. Y equals log 6x. So notice whenever log whenever the base is missing, really it represents base 10. And you'll see this on your calculator, and you'll see this in different places. Some books do put base 10 and some books omit it, but either way, they are the same. How do we take the derivative? Well, again, very similarly. You can either put the derivative over 6x times ln of 10, which becomes 1 over x ln of 10. Again, it's very similarly because it's a constant times x. Again, sometimes I work it out this way. Y prime is equal to 1 over the derivative of log of 6x is 1 over 6x times ln of 10. So this is the first portion. This is just the log. Times derivative of 6x, which is 6. And again, sometimes we can cancel. So we end up with 1 over x times ln of 10. And again, sometimes I work this out this way. And it makes more sense to me because that's how chain rule works. But I also wanted to show how it works in the book too. Okay. Now what about log base 2 of 4x minus 3? Again, a similar idea. It would be, well, should have been, let me try to write this out, y equals to 1 over 4x minus 3, because it's more complicated. Notice how I'm putting it in parentheses, times ln of, this should be a 2. A lot of typos in this section. So it's ln of 2 times the derivative of 4x minus 3, which is 4. And again, maybe tempting to simplify, but nothing you can actually do. So it's 4 over 4x minus 3 times ln of 2. And that's it. Okay. Now, occasionally we'll see the derivatives of ln of absolute value of x or log base a of absolute value of x. The reason for this is, let me try to get to the actual derivative so we can compare. Notice how they are actually the same thing, but let me explain why we would need absolute value. If you recall, in the original ln of x, the domain would have been very different. Because ln of x, you cannot have ln of negative numbers, and you cannot have ln of 0, only positive numbers. Well, 0 we don't have to worry about because x in denominator, you cannot have 0 either. But 1 over x could be negative, whereas ln of x could not be. So there was a big difference in the domain, and when we start studying the graphs of both the original functions and the derivative, then it would present a problem having different domains. Now here there is no such problem. Absolute value of x makes everything positive. Again, we do not include the 0 on both ln of absolute value of x and 1 over x. So that's okay. But again, the domain would be the same. Now we can have negative numbers. But notice how we pretty much disregard absolute value. We get 1 over x. There is a reason for this, because there's derivative of absolute value of x is maybe at some point I will cover it so we actually can derive this. But for now, again, well, we'll take this for granted. Same thing with the log base a. It's exactly the same thing. So if we look at y equals log of 1 minus x in absolute value, notice how, again, I put the derivative. This is how I build it. Negative 1 over 1 minus x times ln of 10. So we could do it that way. Or you can work it out how I did that earlier. Okay? And it works the same way. Now, applications are very similar as with exponential functions. If you have the ln, then we can actually work this out. We'll take a look at just this one really quick. So if we had the revenue function, which is 30 times ln of 2x plus 1, and then the cost is given, how we can find marginal revenue? If you recall, that's the derivative of r of x, which is 30 as a constant. And notice how we had 2x plus 1 in denominator, but then the derivative of 2x plus 1 is 2, so that goes in the numerator. And again, we can multiply 30 by 2, so we get 60 over 2x plus 1. We can find the profit function, which is r of x minus c of x, so it's 30 ln of 2x plus 1 minus x over 2. And marginal profit when x is 60, so we have the derivative of the first part minus derivative of x over 2 is simply 1/2. And then we can plug in 60 for the x. And so we get negative 0.004, or very close to 0 actually, because remember, marginal profit could be decreasing, but very slightly, so it's about 0. And that's it.